All right, welcome to the transformations on the sine and cosine function. So last section we were talking about, last video, not even last section, just last video, we're talking about the introduction to these two new types of graphs, this periodic motion, this lullaby wave, right? You've got your sine that starts up, goes down. You've got your cosine that is just like a giant curvy V, right? And now we're going to go ahead and play with those a little bit. We're going to mess them around. So here I have the equation that looks similar to a sine. It's a 2 sine x plus 3. Sometimes you'll see it as g of theta equals 2 sine theta plus 3. But honestly, those are the same thing. X and theta are acting the same here as y and, and y and g are acting the same here. It's just a variable switch. So don't let, if you see a theta in your homework or on a test or anything, don't let that scare you. It's doing the same exact thing as if it was just x. Okay. All right, cool. So flashback now. Flashback way back to when we were talking about transformations. What does a plus 3 outside of a function do? That's right. It's an up 3. It's an up 3, people. We are right back to chapter 2. We are just going to take the sine function and we're going to move it up 3. What does timesing by a 2 out in front do? That's right. It stretches it in 2. It stretches it by 2 in both directions. It pulls it up and down like taffy. The same exact thing it does to an x cubed. So we don't have to worry about relearning our transformations. Maybe just have to refresh them, right? Okay, so let's start with that sine function there. Instead of being around 0 now, the whole thing is going to move up 3. So I'm going to have it kind of be around 3. Wait a minute. What was that called? Oh yeah, that was called the midline. So the midline in this case has now been shifted to y equals 3. Okay, cool. Amplitude. Amplitude implied it's going to go up and down in a basic sine function. That was just up 1, down 1. Right? Just went up 1 and then came back down 1 and then went back up 1. In this case, that's twice as much. So instead of going up 1, it's going to go up 2 and down 2. Up 2 and down 2. And that is, by definition, the amplitude. And so we're going to go up 2 to like there and down 2 to like there. I'm putting in little dotted lines so we can see maybe where this function is going to fit. Now, the period has not been changed. The period is like a left-right stretch. That is a new one for us. It has not been changed yet. There's nothing around the x to indicate this period is any different. And so it will stay at 2 pi, and therefore the frequency will still be 1 per 2 pi, or 1 over 2 pi. We'll come back to that in a second. So we're still going to end up hitting 2 pi. So we're going to start here at 3, go, let's see, up 2, back to 3, down 2 to 1, and back up to 3. And we have that same size function, same sign, same size. It's just up and a little bit taller. It's going 2 up instead of 1 up. Now, in our last example, please remember we actually used like 1, 2. Anyway, so it doesn't look much different from the last one, but it's stretched. It's doubled, okay? And there we have our 2 sine x plus 3. Okay, has this been shifted either vertically or horizontally? Yes. Yes, it has. It has been shifted vertically by placing a plus 3 on the end. All right, not too bad, not too bad. Let's try out this cosine function now. Remind us, everyone at home, what does a negative out in front of the function do? That's right, it flips it over. I hope that's what you said. It flips it over, and so our cosine function is now not a v, but more of a hill, right? It's more of a hill this time. Now, what does this thing do? This thing is new. This one we did not talk about with our other functions. Oh, no, it's not. I apologize. This one's not the one that's new. This is just a horizontal shift. This is the same thing as a left-right. And since it's negative, which one is it? That's right. We're going right pi over 2. So everything cosine has been moved right pi over 2. There's something else that could affect that, but it's not in the right spot. So I apologize for mixing that up. This is just a shift right pi over 2. All right, so cosine now is still going to be centered around the middle. We didn't add anything to the end here, and therefore our midline was not changed. Our amplitude is now going to be still 1, right? We just flipped it over, but it's still going to go up 1 and down 1. So we'll put -1 and 1 here. The period has not been changed. It's still 2 pi, and therefore the frequency has not changed. We're still going to have one wave in 2 pi, or 1 over 2 pi. And we'll come back to the last question in a second. Now, normal cosine starts up here, but it has been turned upside down. So this cosine will start at negative, go up to 0, up to 1, down, and down. And we can see more of a hill this time, a hill that's going to bounce back in both directions, okay? And so we get an upside down cosine. Here's the thing, though, I didn't shift that. So we're going to erase that, and we're going to shift that whole thing over by 2 pi. So all these points are going to shift over 2 pi, and we actually end up with, this is our hill, right? And then the hill goes off screen. But remember, there's another hill on the other side that is also being pushed up. So now, sorry, I'm going to fix that guy. This is what our function would look like. Never take notes in pen, people. All right, so we've got our shifted cosine. We moved it over to the right, pi over 2, and we turned it upside down. All right, was it shifted either vertically or horizontally? Yes, it was shifted horizontally by pi over 2 to the right. What's cool about this, though, is we could also get the exact same picture if we push it over not just 2 pi, but 2 pi, I'm sorry, not just pi over 2, but also 2 pi and pi over 2. So we could push it over 5 pi, and it would be the same picture, right? Because it's that same periodic motion. If you think about waves, it's a lot of repeated image, right? So you could have different horizontal shifts, like different numbers in there, and actually get produced the exact same picture. It's pretty fun. All right. Let's try a couple more. This one has a little less going on. 1/2 sine x minus 3. Yes, 1/2 sine x minus 3. I really recommend you pause this video and try this one on your own and see what you get. All right, I hope you had a chance to pause the video. Here we go. Now I'm going to try and just pick out the answer to these questions before I graph it. So what is the period of this function? 2 pi. That has remained unaffected. What is the amplitude of this function? 1/2. How do I know that? Because this is a stretch, and a stretch is going to affect how far up and down it goes. It's going to match that number. What is the midline? Y equals -3. How did I know that? Because this is going to take that y equals 0 and move it down 3. That's what a shift down 3 does. And so I can automatically pull that out. What is the frequency? I can just take the period and put it 1 over that. 1 per 2 pi. Has it been shifted vertically or horizontally? Yes, it's been shifted vertically, down 3. Cool. I don't see anything in a parentheses, and so it has not been shifted horizontally, which is good. All right, sine is going to be settled around -3 now. It's only going to go up about 1/2 in both directions, and that is what it's going to do. So up, down, down, up. Oh, it's skinny. It's nice and flat. Boop. And then we're off again on both sides. And there we have a very squishy sine function. All right, hopefully you got the same thing I did. This last one in the video that I want to talk about before we go to some extension ideas is what happens if you try to change the period. So here I have y equals 2 cosine theta over 3. Now notice this is not the same as y equals 2 cosine theta minus pi over 3. Not the same thing, okay? The one on the right is just a horizontal shift, okay? That's a right pi over 3. What this one does, this is something new. This is something that is applying a stretch not to the vertical, but to the horizontal. Okay, it's very hard to do this with a regular function. It's very easy to do this with a cosine function, with a sine function. And so what this is going to do is change the period. All right. Now, what is this number going to do? Boring old classic, make the amplitude 2. Okay, there's nothing on the end. Midline is equal to 0. But when it comes to the frequency, normally we would say it's 2 pi. But now I'm I'm going to rewrite this just a little bit so we can see something a little clearer. Not coup. This pi over 3 is the same thing as 1/3 theta. Okay, 1/3 theta instead of theta over 3. What that does is take pi, 2 pi, and divide it by that 1/3. Okay, it's stretching it out so that it's going to be longer. It's going to take, it's basically 1/3 as fast, right? Because waves move as a function of time. And so 1/3, we've talked about this with rationals, right? 1/3 represents faster, represents, well, no, actually represents slower. It's going to be 1/3 of the time. So it's going to be longer. Now, if we simplify this double fraction a little bit, because let's be honest, that's ugly. We have 2 pi divided by 1/3, aka 2 pi times 3. In other words, this period's going to take 6 pi. It's going to be 3 times as long before a wave is completed. So we've stretched the wave out so that it's really long. It's 3 times as long. It got divided by 1/3, so it's 3 times as slow. Okay. If you had, for example, a 2 pi there, or 2 theta, pardon me, a 2 theta there, it'd be twice as fast and we'd actually get shorter. Okay. But this one's really long. So what I'm going to do is I'm going to be very careful here, and I'm going to evenly spread this out so that I can see 6 pi on my axes. So here's my x-axis. Let's see. 1, 2, 3. I think there's about 30 dots here. So I'm going to count out 24. Sorry about that. I'm going to count out about 24 and then make every 4 boxes a pi. So 1, 2, 3, 4. This is going to be pi. 1, 2, 3, 4. Here's 2 pi. 1, 2, 3, 4. Here's 3 pi. 1, 2, 3, 4. Here's 4 pi. Whoopsies. 1, 2, 3, 4. Here's, wait, 1, 2, 3, 4. Here's 5 pi. And 1, 2, 3, 4. Here's 6 pi. Did I get that correct? Yeah. Okay. So I got my 6 pi. That way, when I look at my wave, it's got to reach. It's got to end right here. It's not going to end back here at 2 pi. It's going to end all the way at 6 pi. So I've stretched it out. Now, the amplitude was also affected. We're going to go up to, let's call this 2, and that one, -2. Okay, it is a cosine function, so it's going to start up. No other transformations were applied. But now again, I have to think in fourths, right? By the time it finishes, it's got to be back up here at 2. So what's halfway? That's going to be 3. That's going to be down all the way, right? And so I can only plot those 3 if I'm comfortable with that. At 1.5 is when it hits 0, and at 4.5 it's going to be where it hits 0. And I may have counted my axis a little bit wrong, but you get the idea. I get this a very big, very stretched out, right, cosine function, but it's still a cosine function. All right, now for the frequency, don't worry, it's just going to be 1 per 6 pi, as we figured out, or 1 over 6 pi. Sorry, not a p. I don't know why I wrote a p. Pi. There we go. Does it have a shift, either vertically or horizontally? It actually doesn't. Remember, shift means movement. This has been stretched in 2 directions. It's grown, but it has not actually shifted. The shape changed. Okay, that's the last one for this video. We're going to do kind of the flip idea in the next one, kind of talk a little bit extension ideas, and I will meet you